Cool. All right, well, in which case, shall we get started?
Sure thing.
Cool. Okay, well, fabulous. Thanks everyone for joining. As for a quick update on Armv9 and the security features that we're bringing for Chromium. So I'm Richard, I'm with Arm based in Cambridge, and Adenilson, you're in California.
Howdy.
Cool. So we're the team in Arm that look after Chromium and its related projects like Electron. So we've got a couple of new joiners this year. We've got, in addition to the people who were here last year, we've also got Andre and Salome, so welcome. Our mission is to make sure that Arm is the best platform for browsing the web. So that involves super high performance on all Arm systems, as well as ensuring that we have really strong control flow integrity through BAC and BTI, as well as making sure that we have really good memory safety as well. So we'll be talking about all three of these areas in this presentation. So over the last year, we've been working on some performance issues. So we've had a revitalized HTML document parser. There's a lightning talk about that tomorrow. So if you're curious, check that out. Adenison's been working on some cutting edge zlib stuff. Most of our year, though, has been steadily adding PAC, BTI, and MT support for Chrome. So, Adenilson, do you want to talk us through PAC and BTI?
All right. So a quick reminder. Last year, we did a presentation where we explained those technologies in further detail. But for people who are unfamiliar with, PAC stands for Pointer Authentication Code, and BTI stands for Branch Target Identification. There are both new features in the ARM architecture that helps to mitigate some security issues. Specifically, BTI helps to prevent JOP or JOPS, which stands for Jump-Oriented Programming, and PAC helps to mitigate ROP or Return-Oriented Programming. The basic idea is that in case of BTI, a JOP will exploit that some instructions like BL, BR, BLR, BLX can target an execution address within the same exception level. So how can you prevent that happening? Basically, you can only branch if you have a landing pad. So if you look on the right side of the slides, the main function, when we call the do something, at the start of the function, there's the BTI instruction, right? And for case of PAC, it will add a signature to a pointer, top bits, the ones that are unused, which allows you to sign the pointer using the original stack pointer plus a hidden key. By standard, there's going to be a Karma cipher, but that's configurable. And the alt star instructions that allows you to validate the signature and will return a valid pointer if everything's right. Otherwise, it will generate a pointer that will have a pattern of an invalid address, thus generate an exception. So together, both PAC and BTI, they will help to strengthen control flow integrity, making harder to start sandbox attacks. Next slide. All right, so we could deploy PAC without BTI because PAC has a better interop capability. You can interop nicely with non-PAC code, given the exception that the non-PAC code will not have PAC security. But BTI, on the other hand, because it's related with branching, requires that the whole binary, every single object file in Chromium has to support BTI. And to make that happen, that requires to use the NDK R23, that requires that all third-party libraries have support for BTI. That also requires migration to compiler RT and libwind, because libgcc on Android is really old, doesn't have support for those new features, and so on. Next slide. All right, so 1 year ago, we explained that in very high level, PAC is just like a simple compiler flag. But BTI is just a little bit more evolved, and 1 doesn't simply enable BTI. Next slide. So what is the current status? For PAC, we have it pretty much done. We already have a compiler flag that can be passed when we're configuring Chromium to build. For BTI, it's mostly done in the sense that we are working both upstream and also downstream to add support for BTI on the missing bits. Next slide. So we have now a new configuration flag. It's ARM control flow integrity. The default is standard. So when you pass that, when you are configuring Chromium, that will integrate with V8 that will turn on support for PAC BTI on inside of V8 and the generated code. We'll also add the compiler flag for all C++ files. And eventually, we hope that it should become the standard when you build Chromium for Armv9. We also made changes to some libraries like libdave, breakpad, and libunwind, adding the missing pads on for BTI support. And we also moved the Chromium to build and run by default using compiler RT and libunwind on Android. And we are also working to migrate to the latest NDK. Next slide. All right, so what is still missing to do? We have to update the compiler to chain package, as also finalize a crashpad support, upstream some of the BTI support to FFmpeg that is ongoing, and I think 1 patch has been merged already. We're confident that by the end of the year, it should be possible to just say check out Chromium, and from the top of the tree, generate a APK for Android, having support for both PAC and BTI. We still have some questions concerning how deployment will be done. One thing I didn't mention, but the PAC instructions and the BTI instructions, the majority of them should be backwards compatible, in the sense that if, say, you are running on an older implementation of the ARM architecture, those instructions, they become NOP operations. But one research area that we're having a look on is to better leverage PAC, made it even stronger by signing things like virtual function pointers. And that pretty much covers PAC and BTI.
Cool, awesome. So I think to talk about the other feature, which is MTE, I think we should kind of start off with why we think memory safety is important for Chromium. So we presented a similar slide to this one last year about all of the issues that have been picked up by the address sanitizer. So we see the usual kind of use after free, suspects. But actually, this was a mid-cycle update. So actually, there are even more issues fixed by the M95 initial release. So we have, for example, the heap buffer overflow in Skier. We have use after free in various areas, all kind of high, medium severity. We have an out-of-bounds read in web audio, use after free in PDF, accessibility, use after free in profiles and network APIs. So, this is quite a common form of security issue that hopefully MTE will help address. So by my reckoning, out of sort of 22 medium-high CVEs disclosed for M95 so far, about 13 were related to memory safety issues. And we think that the current implementation that we've done in Chromium will hopefully target about 7 of those. So it's good news, which is that we're reasonably confident that MTE can help find these sorts of memory bugs, because actually we've already found one before it was merged, or Peter Collingbull at Google found this one while testing out our MTE patches. So to give a very high level overview of what MTE does, under MTE, basically every 16-byte region of memory can now have one of 16 different tags, and we store those tags in the top bits of the pointer. We also store them in a kind of shadow area of memory that's not normally accessible. And every time we load or store a pointer or manipulate it, we check whether the pointer's top bits match what's in the shadow area. And if we detect a mismatch, then we crash, either eventually or immediately, depending on the mode that we're in. So we probabilistically detect use after free and buffer overflows in production software like Chromium. We have kind of two main flavors, heap tagging and stack tagging. Stack tagging is a bit more specialized. It requires a specific build. So we've implemented heap tagging because it's backwards compatible and can run on all Armv9 devices. And there are two primary modes for MTE as well. So synchronous mode and asynchronous mode. So synchronous mode is very good for debugging. It means that you can get a precise stack trace immediately as soon as the memory issue occurs. Async is much higher performance, but it's harder to debug. So you don't always get the precise stack trace every time.
Richard, 10 minutes.
Sure. Thanks, Adenilson. So to describe roughly what we've done, you can kind of think of the logical organization of the partition allocator's memory as something like this. So within each partition, there are buckets, slot spans are in buckets, and slots are the kind of fundamental unit of allocation within the partition allocator. And essentially, when we provision these slots, we tag each slot randomly. So once we've pre-tagged these slots, we can then give back memory from those slots, and it's imperceptible to the majority of the Chromium code base. The only difference is that it has a high bit set. Then when we free and return stuff, we then increment the tag. So we kind of revoke the slot tag for that given thing. And this means that when we attempt to write anything to a freed pointer, we'll detect that as a memory safety issue. And similarly, if we go too far beyond the end of a slot or too far before a slot, so for example, if we have a heap buffer overflow, then again, MTU should be able to pick that up because the adjacent slot is tagged, should be tagged most of the time a different color. So we've kind of taught the partition allocator so that adjacent memory areas are tagged differently most of the time. Free memory areas are always tagged differently every time. So this should get us mostly to where we need to be to detect use after free areas more reliably and consistently. We do have some limitations, so we only tag objects less than 1500 bytes. We don't protect anything on the stack or global variables or anything like that. This requires a special Chromium build. We have looked into using MTE in other areas of the browser, such as V8 and CPPGC. We're pretty sure that those require separate builds, though. Also, we don't protect any metadata in the partition allocator at this point. So once you have a valid pointer to a slot, you can manipulate anything that's reachable from that slot. So last year, we also presented this slide, which talks about the various deployment options for MTE. So we can go for a synchronous mode, which is faster but less precise, and synchronous mode. And within each of those areas, we can either choose to tag more, allocate more, and detect more. So to give you our current thoughts on MTE deployment, at the moment, we're planning to make sure that every time you execute a unit test of any sort on an MTE capable device, you'll get synchronous MTE by default. So that should enable us to debug and find issues quite quickly. For the browser process itself, we must always start the browser. We must always start the browser in async mode for MTE to work correctly. And then we can either choose to upgrade to stronger MTE if we need more guarantees, or we can turn it off. So for example, we might switch it off for the renderer process, or we could upgrade its strength for the browser process. And so we do this through the Android manifest.xml. There's a new tag that we can opt into. And on Linux, you can set it using the environment. So there's a glibc tunable, which allows you to opt into various MTE modes. So we also talked about our plan for kind of shipping MTE in Chromium. We've mostly managed to stick to the plan. So we've implemented support in the partition allocator. We've added functions to enable this throughout the code base. We also have been working very hard with the Android folks at Google to make sure that Android S is available and tested against this. So we've also had a couple of other requests in the Chrome memory team to look at exploring ideas to make sure that PC scan and backup ref PTR work and could potentially be more efficient with MTE as well. I'm particularly interested in fuzzing enablement for this, so preparing experimental builds to find more bugs. And also we've had a request to do some debug tools. So for example, when we detect a memory safety issue, can we print out a nice stack trace of where that area was last allocated and freed? So we're working on that as well and trying to find a good solution that doesn't cost too much in terms of performance. Cool. So with that, I think that's all the content in this presentation. So shall we turn to the chat and see if we have any questions? I'll stop showing the slides so we can have a QA session.
Ooh, trippy.
Yeah, Hall of Mirrors selection. So let's go have a look at the chat and see what's up.
Yeah, it seems that there is a Q&A feature, so people could click on ask a question, I guess, or just go on chat, whatever.
Cool. Yes.
First question. How do these hardware features interact with efforts like Miracle Pointer?
Cool. Yeah. So that's a good question. So Miracle PCR is a very interesting project in that it kind of covers all Armv9 devices. So MTE is kind of built into the hardware level, so it doesn't require any particular kind of C++ annotational work. So it doesn't rely on compiler instrumentation or anything like that. All code is covered, including assembly code. So it's a more kind of general technology than just Chromium. So one interesting area that I'd like to look at particularly is the idea of kind of quarantining less frequently. So for example, there's a kind of scanning operation where you scan the stack and some globally known objects and check essentially that no pointers hands remaining inaccessible. So potentially we could reduce the frequency that we need to do that under MTE, because we can reasonably guarantee that any pointers which are freed are not usable in the sense. That said, Miracle PCR has more of a security focus, whereas we have more of a bug finding focus. So Miracle PCR is making provable guarantees about non-exploitability of use after free, whereas we are kind of more like a faster address sanitizer in that sense. So it doesn't necessarily give you. Sorry, go ahead, Adenilson.
Yes. Aside that, I believe Miracle Pointer only applies for heap memory, right?
Yeah, so MTE does have the potential to cover more memory safety areas than something like Miracle PCR, with stack tagging especially. Again, the issue with that is that these new MTE instructions are not space encoded like PAC and BCI are. So as a result, in order to use stack tagging effectively, you have to have a separate Armv8.5 specific build. But this is similar to any kind of debug build or something similar to that. So
also, I believe that PAC BTI should be able to address cases of, say, stack corruption.
Yeah, so definitely the stack corruption, which really affects control flow, the one that you have to watch for is definitely overwriting the return pointer, and PAC helps massively with that. So that is a kind of provable security guarantee that you can depend. And the MTE, as ever, when there's a difference between your test binary and production, MTE can help you find issues that might affect the stack more often. But yeah, it's very interesting to see if we could, for example, do kind of streamed builds that are MTE specific. But for now, we're planning to be fully backwards compatible.
Okay. We have another question. So which ARM platforms is this available on in practice? Beyond Android, is it available on Chrome OS, Mac, and Windows ARM devices?
So Windows, no, at the moment. But it is also available on Linux. So there's, I think, essentially we're kind of launching on Android first because it has the most kind of complete support for MTE. similarly, all of the kind of kernel work for MTE is done. So Linux is an easy target for MTE as well. I think support for other ARM platforms is possible, but at the moment there's no kind of so MTE hardware is planned in the kind of mid future. So basically, other platforms will come as hardware that supports MTE becomes available.
Yeah, I mean, that being said, Apple Silicon implements Armv9, which should have support for PAC. So we could in theory enable PAC there, but it doesn't have support for BTI, and the plans to have them both.
Yeah, so they also have a separate ABI, which is different from the Linux ABI. So we have a very backwards compatible ABI at the moment for PAC and BTI. There is discussion about having a stronger ABI, which makes better use of PAC, and so we kind of alluded to that on the slides.
All right, so we have another question here. You mentioned that a special Armv8.5 builds would be needed to extend protection to V8, CPPGC, etc. Can you elaborate on why?
So V8 we know requires a separate build, essentially because MTE relies on having 64 bits in the pointer, and one of the optimization techniques that the V8 team use is essentially pointer compression. So they kind of locate everything within 4 gigabytes, and the majority of pointers in V8 are 32-bit. So this doesn't play very well with MTE. Having said that, it is we've done some interesting experiments with the V8 team. I should probably bring one of the V8 team into a future presentation that we do on this, and they can talk about the interesting things that they've been doing with MTE. CPPGC is more interesting, and I think it's more of so it's definitely more of a research area. We decided to do the partition allocator first because it's kind of much more traditional. MTE heap tagging is kind of very much designed for that kind of malloc and free paradigm. So there are some interesting things we could do with CPPGC. So for example, we could in each garbage collection pass, we could, for example, retag objects that we know are live, do some interesting things like that. But as well, I think we have to pick the areas where we know the majority of the bugs are, and I think for CPPGC, it's already reasonably hard to exploit, so we focused on the partition allocator first.
All right. Any further questions? Nope.
Cool. Okay. Well, yeah, fantastic. Well, thanks for joining. Thanks for co-presenting, Adenilson. Yeah, we'll have a great BlinkOn. We'll see you soon.
Oh, yeah. Bye-bye.
Cool. Thanks. Bye.